Okay, perfect. So, hello everyone. I'm James. I'll introduce myself in a second. This is to talk about Monte Carlo sims in DuckDB. I'll explain why it's a bit crazy maybe in a little bit, but hopefully it'll be interesting. So, first of all, I think a really massive thank you to Marcelo and Mihai for putting this together. I run a data meetup in Dublin. It's really cool to see more technical data meetups here, especially we've got a lot of people in a lot of different companies who use data all the time. But if you look at the footprint of meetups in Dublin, I don't think it represents the size. So really well done. And thank you so much for putting it together. It's amazing. Okay, so what am I going to try to communicate in this? Basically, I'm going to say, what is a Monte Carlo simulation? Why are they useful? Why does efficiency really matter in them? And then finally, the actual kind of thing that I want to get people to take away from this is, how does DuckDB compare right now to other Python tools that you might use? So just a quick question, which is, anyone who's familiar with what a Monte Carlo simulation is, could you raise your hand? So there's a few people. Okay, cool. So hopefully I'll explain that well. So who am I? That's me. So what do? I'm a quantitative data engineer in a company called Susquehanna International Group, which is a trading firm actually just down the road. I guess I should also put in a disclaimer that this is mostly from a hobby side perspective rather than me representing the company or anything. That's my day job. I used to be an engineering manager in a company called Conjura. Conjura actually had DuckDB running in production in some of our very important microservices, which I was lucky enough to be able to implement, I guess. So that was in August of 2022 for a little bit over a year. And that was a real success story. That's kind of where most of my hands-on experience with DuckDB is. I'm from a theoretical physics background, which is why the Monte Carlo stuff is maybe appealing to me. And I'm a DuckDB fan. And that's kind of it. So, okay, let's talk about what these Monte Carlo simulations are, right? So who here has seen Star Wars movies? Okay, lots of hands. So there's this famous scene in Star Wars Episode 5 where Han Solo is piloting the Millennium Falcon, trying to get away from the Empire, and C-3PO and Princess Leia and Chewbacca are all on the ship. And Han Solo, in trying to get away, drives into an asteroid field. And C-3PO goes, the possibility of successfully navigating the asteroid field is 3,720 to 1. And, looks very concerned. Then Han says, never tell me the odds or something like that. And they all fly away. So my question is, how does C-3PO get to that number? Right? So maybe what C-3PO is doing is he's going, well, let me think about what might happen. And I know how big asteroids are. I know how fast they move. I know how quickly a human can react. And so I'm going to make a simulation in my head with all of these probabilities about what might happen. So maybe C-3PO will go, oh, well, we'll just run into an asteroid. Or maybe C-3PO is like, oh, a TIE fighter will shoot us down. And maybe we'll get right to the end, and then we'll go into another asteroid. Or possibly we'll get away, right? And so what C-3PO could do to estimate that probability at the start is basically run through all of these possible simulations in his head and then look at how many times the outcome happened, in this case, the Millennium Falcon escaping, versus how many times it blew up. And so that is basically what a Monte Carlo simulation is, right? So here C-3PO, to get that number, is going to simulate what's going to happen and then look for this sort of observable thing at the end. And the reason that it's very helpful is, there's a lot of probabilities involved. It's kind of complicated to put it all together and to get the mathematical answer, right? So yeah, basically what is a Monte Carlo simulation? It's kind of an approach for solving very difficult or impossible math problems, fundamentally. It relies on random sampling. So if you can see here, this isn't my plot at all. I put the link down below. And this is something to estimate pi by throwing dots at a one by one square, and as if it was a dartboard. And you can see as you kind of increase the sample, you get a denser and denser distribution on this thing, and you can use that to generate the area and therefore the pi, right? This mathematical constant. Where is it useful? Well, so I did a bit of Googling, and so I kind of made a collage of everything. So on the top left, you've got theoretical physics, then cosmology, the top in the middle, top right is computer graphics, legal studies. Over here, I should use the pointer. Legal studies here, like pharmacodynamics, finance. It's kind of everywhere, right? So, yeah, it's pretty much everywhere, because a lot of the time we've got these very complicated mathematical things. We don't know how to solve them, but we really want to solve them. Okay. Why is efficiency important in these Monte Carlo simulations? Well, let's think back to that C3PO example. We're, getting all of these samples, maybe C3PO does it 10,000 times and comes out that the Millennium Falcon survives 3 in those 10,000 times. There's going to be an error associated with how likely that estimate is. And that error, it turns out, is this thing called the standard error of the mean. And you can see that it depends, I'm not going to derive this right, but it depends on the square root of the sample size, or n, that you're using. Basically, as your sample gets bigger, intuitively your guess gets better. And so we really care about efficiency from that perspective. In a practical use case, what does efficiency mean? It means we kind of care about a certain amount of accuracy. And so if we're running on a cloud, to get that accuracy, we have to scale our sample points and spend more. So if we're more efficient, we can get more sample points, maybe without spending quite as much. If we're on premise, we now have much more resource that we can use, but we're often on a fixed time budget. So one of the examples that, Monte Carlo sims are useful for is predicting weather forecasts. With the weather forecast, you got to go on the news at 1 o'clock and say what the weather tomorrow is going to be. And so if you just have more efficiency, you can start to kind of generate more and more of these samples. And so what we really want to do as people writing technologies, we want to maximize the accuracy of the results that we're generating. We want to minimize the time that it takes to do it. Another aside that I was just thinking about as I was going through this stuff, and I tried to do like some estimations. So supercomputing, like Monte Carlo sims, are this like very unknown thing in my opinion, but it's like a really huge proportion of actual like computation in the world. And so I found this paper over here, which was in Nature Astrophysics, looking at the kind of emissions projections of Australian, astrophysics workers, like research scientists. And so, yeah, supercomputing is a really dominating factor in their carbon emissions. And I actually just kind of did a quick estimate. So this is from UNICEF in 2018. And so this is the number of research scientists per million people. So if we multiply that out, say about half of them are using Monte Carlo, or like using supercomputing or Monte Carlo, use this number up here for the emissions, which is the 20. So we get, basically, roughly speaking, when we add some other people who aren't research scientists, about 200 million tons annually of CO2 from supercomputing. Try to kind of keep it in perspective. It's about 5 times what Ireland does. And so, there's other things other than technology that building efficiency in this sort of field is really helpful for, in my opinion, at least. So yeah, now let's come back to our question. So now in a parallel universe where Han Solo really cares about the probability, and let's just assume that C3PO is written in Python, because I'm a Python developer. Yeah, everything's written in Python, right? So what should C3PO use to generate this Monte Carlo sim? Well, if you ask ChatGPT, ChatGPT will say, use NumPy, right? You will also, if you start Googling around, you might find some stuff about Numba. Polars, if you Google just fast stuff in Python, you'll get polars a lot of the time. And my question is, well, where does DuckDB fit in here? And I actually, at this point, need to acknowledge there is someone in the States who has done this before, as in Monte Carlo in DuckDB, a guy called Jacob Matson. He's got a project called the Modern Data Stack in a Box. He's coming at it from a completely different angle, in my kind of outside opinion. So he's using Modern Data Stack in a Box as a proof of concept for how you can gel these open source tools together. One of the things that Monte Carlo is really good at is generating sample data volume, because you don't have to send the database to someone, you can just generate these random samples. So he's kind of viewing it from a scale perspective. Like there's a blog post on the DuckDB blog that mentions Monte Carlo, but it never talks about how actually useful it is, right? So here I'm kind of coming at a different angle. So let's say these are our 4 choices of tools. There's loads of other stuff that we could use. And really we're not actually choosing a library here, we're choosing an implementation in a different language. So NumPy is written, fundamentally, a lot of this stuff is written in C. Numba actually is a just-in-time compiler, and it kind of compiles Python down to machine code. Polars, its execution engine, is in Rust, and DuckDB is written in C++. Okay, so that's the context, that's the question. Hopefully everyone kind of understands a little bit about why all of these questions are important and useful and impactful. Okay, so how are we going to do this benchmark? Well, I need to say, like, we're gonna do some situations. When you Google it, always the example is to calculate pi, so we're gonna do that, and then we're gonna also simulate the expected values from playing roulette in a casino. We're gonna compare libraries based on their execution time and memory footprint, and our question is not to measure these things directly against each other. It's just to see, is DuckDB viable? Here's some disclaimers. I did this benchmarking on my laptop. It's quite a nice one. It's an M3 Max with 48 gigs of RAM. I was kind of strict, so I said that any number should have 5 samples basically associated with it, so that we have some nice error bars. And yeah, there's some other stuff here about like CPU computation. I think the important thing to note is that really this should not be interpreted as this is better than that. It's kind of, does this belong in this discussion? Effectively, that's what I want to talk about. Okay, so the pi calculation, this is the thing that if I come all the way back to here, this is what we're doing. We're drawing n points, and we're checking if they're inside the circle. So if I come back here, so we draw, some set of points between -1 and +1 in our case. We check if the sum of their squares is, or actually no, we're going to draw points from -0.5 to +0.5, I guess, and -0.5 to +0.5 in the y-axis, and we're checking if they're basically inside this radius of 1. Maybe I've messed that up actually now that I think about it, but there's a formula we can do, right? You can write this in a SQL query using stuff like generate series. I haven't actually written any of the SQL here because it's not an easy way of putting it in the code. But so what I want to talk about now is let's just look at some results. So it's a really simple operation. And the answer is really clear, right? So DuckDB is rubbish, we should all go home. So DuckDB is taking 20 seconds here on the 1 billion amount of data volume versus Numba, which is very quick. Takes about 4.5 seconds. NumPy 9, so these are all these numbers down here. The columns are sample sizes, and then the error bars are from the kind of sampling. Okay, so this is a simple thing, and you would actually expect Numba to do well here typically. And when you think about what is DuckDB good at doing, we always talk about it's a database, and this is what, when ChatGPT answers the question, should I use DuckDB? It'll probably say no, because it's got all of this joins and group bys and all this sort of stuff, and none of that is being used here. So it's not entirely unexpected that it's not doing so well. There's actually some nice things that we can see as to why it's not going so well. So this is, memory consumption as per a Python developer. So please do not immediately trust these numbers or any interpretations. But this is from a memory profiling library in Python. I think it's called Memory Profiler or something. And so over these sample sizes, we can see here that DuckDB is basically using about the same amount of memory each time, whereas when, let's say, NumPy scales, we see it scales very aggressively and uses up a lot of this available RAM. Similarly, if we look at the median, basically the shape of these charts we can infer. I've actually got a chart of that here. So we can see over time on this axis how everything kind of comes up apart from DuckDB, which I focused here on in this blue line. And this is actually something that we'll see, and I think it's to do with how DuckDB aggregates, and we'll come back to that at the end. So yeah, pi case, DuckDB maybe not so good. Yeah.
Either a billion floating point number, right?
It actually 2 billion for the case, because we're doing it on an XY plane. So we're generating a tuple each time. But yeah, they're floating point, and it's just a uniform distribution, 0 to 1. And so DuckDB has an inbuilt function to do that. It goes into the standard library. NumPy does something similar, I guess. Python has its own thing. For, like polars, I haven't really spent a huge amount of time kind of tuning up, but polars doesn't have that sort of thing. And so there you need to use the NumPy implementation to generate the data, and then you pass it into polars, if that makes sense. Okay, cool. So our second case is this roulette simulation. These are the rules. If someone hasn't played roulette, I've never played roulette in my life. So you basically have it's slightly unlikely for you to win, right? So this is a useless simulation. We know that the actual reality is you should not play roulette because the house wins. But the point of these things is you could test different strategies if you wanted to. So if maybe instead of saying it's a 10 euro payout either way, you could maybe say, okay, what if I have to pay €1,000 in, but now I get a 10.50 payout and I lose 10 euro. How many times do I need to play to make that worthwhile? You can start to test out all of these sort of strategies, and that's why one of the reasons as to why these things are very helpful in finance, for example. So we have lots more parameters in this one. We can sample many times. So we can have, 100,000 people who start with €1,000, and we can see how they do. We can always also kind of increase our data volume by going out to a different time horizon, maybe 1,000 turns, 3,000 turns, 5,000 turns. And then there's two kind of different versions that I've benchmarked on. There's one where we return every amount of money after every turn for every player, and then one where we basically say what is the average and the error associated with that average as we go and kind of come back across the data set. And actually here, it's a much different story. So this is the execution time for 1,000 turn kind of time limit, unaggregated, and we can already see suddenly DuckDB is very competitive actually compared. And so really what we'll see here is that the main rivalry is between DuckDB and NumPy. NumPy is what ChatGPT will answer if you Google this stuff as to what you should use. And so DuckDB in this case is already better. In the aggregated case, it's slightly worse, but still comparable. And then it gets, it kind of continues that trend, right, for the case when we expand out to a different time horizon, 3,000 turns. And then finally, in the case of 5,000 turns, we actually see it starts to do really, really well. And so here it's significantly faster, in my opinion. Like, we have to always think back to sample size, right? So these things are generally linear. So if you're twice as fast, it means you can take twice as many samples in our sort of like cost optimizing, which means that your kind of accuracy of measurement will go up, significantly. So we can see that, DuckDB is now suddenly faster on the aggregated side, and it's a lot faster on the unaggregated side. There's actually helpful visualization we'll see, but I guess one important thing is that these longer term strategies like 5,000 turns here, in the case of this example that we're actually running, again, it's irrelevant. We know the answer. You can see the downwards trend if you look at the numbers that these are generating, but these are very helpful when you have strategies that maybe don't converge as quickly. And it's very, very statistically quite noisy. It's meaningful to have accelerations at this sort of scale. Let's look at the memory profile. So this is the 200,000 samples up to a 3,000 turn limit. So you can multiply those numbers together to see how many like floating points we're using here, basically, roughly speaking. So that's I guess, like what, 800 million? No, maybe not. No, 600 million, right? Maybe I'm missing a zero. So DuckDB is here in the blue. It kind of does what we would expect, right? Its memory footprint increases over time, and then it dies away. NumPy kind of comes up and then comes flying up. Polars is just kind of chilling out up here. NumPy, I haven't really tried to optimize these guys, so I think these would be better if there was more effort put into them. But yeah, the comparison really to focus on is, DuckDB does quite well. Actually, in the aggregated case, DuckDB performs this same thing. So I think this memory thing is actually a red herring. But yeah, so this is a case where I think DuckDB is almost as fast as NumPy, but its memory sort of profile looks unpromising, and we'll actually come back to that at the end in terms of conclusions. But yeah, so here in terms of scalability, like so maybe DuckDB is, appropriate for this sort of stuff. How might we be able to scale it? Well, everything is kind of single node. The way I've done it in Monte Carlo sims, it's fundamentally scalable because you're just doing these random samples. So you can scale laterally extremely easily. You can generate, you can spin up 10 boxes and to do the same sample, it's exactly equivalent to doing it on one, and they're completely independent. So you don't really have to care about the network overhead. There's no coordination needed. So yeah, here, there's like not much CPU pressure in most of these. It's mostly memory pressure. Just this is me looking at the activity monitor on my Mac. And so I think you could like very aggressively multi-thread if you wanted to on the DuckDB side, because there's this memory, there's not super high memory usage, even for these longer samples. And then, yeah, in terms of scalability, when we come to this, like, let's imagine we spin up 10 laptops to make 10 times as much data, and now we generate 10 times as many raw files. Now there's some very nice features that DuckDB has, for example, filter pushdown and like distributed query behavior, where we can now aggregate these things up quite effectively. So there's a few different DuckDB learnings. I'm trying to keep an eye on the time, and I think I might need to step on a little bit, but we've got this aggregation thing here, right? The very flat memory profile. What I think is happening, and again, this is the guess from a Python developer, is probably that because this data is completely ethereal, what I would guess is happening is that DuckDB is kind of computing it right to the end in small batches, and then kind of having some store at the end, and then it's constantly doing it. So it's never holding a huge amount of memory like maybe NumPy is, as we can see. That just means that it's more parallelizable principle, because generally memory, or at least in the example of these cases, it's memory that's restraining it, it's not CPU. Also, just like some very specific things, Arrow is faster than DF for large data sets. In terms of writing out the results, I wanted to keep it fair. I brought everything back to the Python interpreter at the end. For smaller data sets, DF is faster than Arrow for some reason. A few other things, just random bits that I kind of ran into. There's this DuckDB inbuilt thing called like standard deviation function. This is actually the DuckDB web shell that Mihai was talking about earlier. If you use the standard deviation in the as a just a function on exactly the same data set versus writing it out by hand, there's quite a significant time difference. So like 930 milliseconds versus 660. It's just one interesting thing. Again, I guess there's some parallelization happening in here that's maybe not happening in here in the query engine. And oh, oops, one other thing. This is the roulette guy. This is actually some SQL. DuckDB is great because it has a query planner and it'll optimize things, but sometimes there's a skill in actually doing stuff by hand as well. So this casino thing smells like window functions, but if you implement it as a window function, this is just two exactly the same things. This one comes out to be 45 milliseconds. If you implement it as a recursive CTE, it's 27 milliseconds. And again, there's reasons for this, but I won't really go into. So in conclusion, DuckDB is, woohoo, a viable option for Monte Carlo simulations, at least in my opinion. It is better in higher path complexity situations, like when we've seen these long time horizons. Something I haven't really talked about, but it's got this Python function API. And so if you were running into issues where you're like, oh, I want to use this Python function, but I can't because it's a SQL, you kind of can. It might just be a little bit slower, and then that's going to come back to your mileage may vary point. And yeah, this is a really important point because I don't want to be harsh. I think Numba in general will be one of the more compelling ones of this library. I had lower effort to optimize both Numba and polars. I really focused in on the NumPy versus DuckDB comparison. And yeah, I guess the most important point is if you want to run this benchmark suite on your own laptop, I've got it up here, MC-benchmark. I plan to make this more mature over time and ideally visualize it in a better way than just some random tables in my thing. And I guess, yeah, at some point I will probably publish a blog somewhere or a post. I have no idea where somewhere is going to be when I know that there's fair comparisons, because when you Google this stuff, it's really hard to figure out where is where and what is what, and people will say, implement it in C++ yourself, which is crazy in my opinion. But yeah, that's pretty much it. So hopefully whenever you're thinking about running a Monte Carlo simulation to figure out how you can go through an asteroid field, you'll use DuckDB in future. But yeah, that's it for me.